this video, we will talk about the effect of the existing substituents on the ring towards the incoming electrophile. All right, so let's look at an example over here, a general equation. So let's say your ring, you have a substituent called X, and you want to add another electrophile or another substituent, which is an E plus symbol, all right, to the ring. Where would the electrophile be seated on the ring? Okay, the X, which is the first substituent, will influence the position of the electrophile that will sit in. Okay, so that's why we are going to learn what is the effect. Now, the effect, two effects actually. Number one, where does the incoming electrophile sit? Number two, the rate of this reaction. So, as you can see, I labeled in two colors. The first substituent, the carbon, will be number one. Now, you can count clockwise, which is 2, 3, 4, 5, 6. You want to count anti-clockwise, it's still going to be 1, 2, 3, 4, 5, 6 on the opposite side. So, I'm just going to use the clockwise method. Okay, so now, it all depends on what is your electrophile. So I'm going to break down electrophile into two categories, the activators in green pen and the deactivators in red pen. So first, if you identify the electrophiles that they are activator side, okay, it means if your X is activator. So if your X is an activator, therefore the E will sit at position 2, 4, and 6. So for example, okay, there are three activators you need to know. The first one is NH2, followed by OH, followed by an alkyl group. Okay, now I'll give you a very small example down here. Now, if your X happens to be NH2, and you want to add an electrophile in, your electrophile can be any one of the 4 electrophilic substitution reaction. So for example, it can be a Cl plus or Br plus from halogenation. It can be a nitronium ion from your nitration. It can be your alkyl group from alkylation, or it can also be the acyl group from acylation. So any one of these 4. So I'll just generalize them into E plus electrophile. So the first substituent is NH2, which happens to be an activator. Now, if you are an activator on the ring, regardless who is the incoming electrophile among the 4, okay, they will be directed to position 2, okay, 4 or 6. So this is position 2, position 4, and position 6. Okay, so you can add any one randomly. Okay, let me just erase this thing. You can add your chlorine to any one, but you only can choose one. Okay, either one. So if you can see over here, this is position 2, this is position 4, and this is position 6. Okay, you can add the electrophile at any of this position. So let's say I'm going to add it to the position 2. Okay, I want to make it a bit neater. So I would like to add position 2. Okay, why? Because the NH2 carbon is carbon 1. Therefore, his direct neighbor is called position 2. You can put 2, 4, or 6 up to you. And then remember to balance it to show that the proton has been formed. Okay, yeah, so that is activators. Now, same goes to OH. If let's say I erase this to become OH, or like this, or I change this to an R, okay? So regardless whether you are the NH2, OH, or the R, okay, the incoming electrophile will be directed to carbon 2, 4, or 6, either one. Why? Because the NH2, OH, and R are considered as activators. Okay, now let's change to deactivators. So for deactivators case, so let's say your X, okay, and what are the X that you need to know? Now the first one is a NO2, okay, and then followed by carboxylic acid, followed by a COR, okay, like this. Okay, now these are the three examples of X. Okay, so let's say I'm going to put an NO2 here. They are considered as deactivators. Okay, now if NO2 or COH or COR has already been substituted on the ring, they will influence the incoming electrophile in terms of their position and weight. I will discuss position first. Okay, now if you recognize NO2, COH, and COR, please tell yourself this is an deactivator. The incoming electrophile, okay, be it any of the four, you can pick. Okay, so let's say I'm going to pick a let's not put nitrogen, let's put a CH3 LQ group. Now it will be directed to position 3, 5. Position 3 and position 5 is the same thing because there's a plane of symmetry over here. Okay, so let's say I take my black pen. Can you see the diagonal line? Okay, your benzene ring, right? 2, 6 are mirror effect, 3, 5 are mirror effect. So it's the same, all right, if you only have one substituent on the ring. So if your NO2 is a deactivator, your incoming electrophile, in my example here is an LQ group, they're seated at position 3, okay, with respect to the NO2 position. And you balance the H plus out like this. Okay, now, so therefore, you have learned the 3 examples of activator and 3 examples of deactivator. Now, it will be very beneficial for you if you can memorize the ranking. Okay, now, the ranking means if let's say you have 2, okay, you have 2 on the ring and you want to do a third substitution. So, for example, okay, so let's say you have a NH2 here, and let's say you have OH here. Both are deactivators. And then now you want to add an LQ group, a third substitution inside. Okay, so when you have 2 substituents, the incoming electrophile have to decide who to listen to. Should he listen to position 2 with respect to NH2, or should he listen to position 2 to OH? It can be 2, 4, 6. Okay, so I'm going to use different colors to indicate over here. Now, if you want to follow position 2, 4, 6 with respect to NH2, right? So this position is 2, 4, and 6 if you want to be directed by the NH2. So that is the 2, 4, 6 with respect to NH2. But if you want to be directed by OH direction, so if you want to listen to OH, right? This is position 2 and position 4 and position 6 with respect to OH perspective. Okay, so now the question is, LQ group, which is the incoming electrophile, who would he listen? So there's a ranking, if you can see at the top of the page, where NH2 is stronger than OH, which is stronger than an LQ group. So in this case, we will choose to listen to the stronger activator for NH2. Therefore, I will try to substitute at this region, and this region. Okay, now, because the right-hand side has already been substituted by OH, so you may answer either on this position which is position 6 with respect to your NH2, or the other option, the other one, you can substitute the alkyl group at this position here. Either one. Okay, position 4, position 6, because position 2 is already substituted by the OH group. So there will be a mixture of these two isomers, and both of them are considered as positional isomer because the position of the CH3 is different on the ring. So you need to know the relative strength of the activators. All right, so NH2 is stronger than OH, which is stronger than your alkyl group, any alkyl group. Same goes to the right-hand side. Okay, quickly, we will do another example here. Let's do with color pen. If you have two substituents here, okay, so let's say you have the NO2 here, okay, and let's say you have a COOH here, okay, and this time you want to add a bromine electrophile, okay, so NO2 is the activator. If you want to be directed by the NO2, okay, being a deactivator, your bromine electrophile will be seated at position 3 and position 5. Okay, this is position 1, 2, and 3. So this is 4 and this is 5. If you want to be directed by the NO2. But if you choose to be directed by the COOH, so in the COOH perspective, this is 1, this is 2, and this is 3. Okay, so this is position 3 with respect to COOH, and therefore this is position 5 with respect to COOH, because COOH, the carbon there is number 1. Okay, so now you have the black pen version, which is listen to the COOH, or the red pen version, which is listening to the NO2. So now you have to make your decision. Who should the bromine electrophile listen to? Then you must bring your ranking. So you have to memorize that NO2 is a stronger deactivator compared to COOH. Please be directed to the instructions of NO2. So NO2 will direct the incoming bromine electrophile to the carbon 3 and carbon 5 with respect to the NO2 position. So it has to be with respect to the NO2 positioning. Okay, so what is my answer? So my answer I will draw here. So you can direct your bromine here, okay, or you can direct your bromine position 2, position 5. Okay, sorry, position 3 and position 5, right? You can direct here. Same thing, both will be produced, all right, in a mixture, and both of them are considered as positional isomers, all right? So what we have covered so far is we covered what are activators, what are deactivators. Second, we also covered the relative strength of the activators and the deactivators. Okay, yeah. Now, there's one more thing, all right, that I want to add on over here. Now, over here, there is one more exception, okay, and this exception is considered as a halogens. Okay, so I'm going to add one more arrow here. Now, for halogens, right? Halogens, they are considered as deactivators. Okay, but they will direct to the 2, 4, 6 position. Okay, this one is an exception. Okay, so they stand alone in the middle between two. So they are deactivators following the red color pen, but the position they will follow the green color pen on the left. Okay, yeah. Now, so let's do one example of where your substituent is a halogen. So let me draw the ring out first. So let's say your X, the first one, is a halogen. And you want to add, let's say, an acyl group here, acylation. Okay, now first, bromine, chlorine, okay, and iodine, they are the deactivators, but they will direct to the 2, 4, 6 position. So where is 2, 4, 6 position? with respect to the bromine, this is position 2, correct? Or it can come out position 4. It will be a mixture of these two, same thing, positional isomers. Okay, we know halogen are the activators, but they will direct the incoming electrophile to the position 2, 4, 6. 2 and 6 are the same. Remember, 2 and 4, 6 is the same thing. All right, if you flip it, because there's a plane of symmetry over here. Can you see the plane of symmetry? Okay, yeah, I dot the blue color line. All right, so you substitute at position 2 or position 6, they are mirror effect. Okay, either one. All right, so that is the exception of your halogens. Right, so I have covered, okay, what are the effects of the substituents on the incoming electrophile in terms of position. All right, so we know that activators direct to 2, 4, 6. Deactivators will direct to 3, 5. You also learned, okay, on the relative strength of the activators and the deactivators. Okay, now, in terms of rate, it will be quite straightforward. Okay, it will be quite straightforward. If you are an activator on the ring, that means you have substituted on the ring first. Now, the subsequent substitution will occur at a faster rate. Okay, so now let me give you an example in terms of rate. How do we explain it? Okay, now in terms of rate now. Okay, now let's go to activators example. Okay, if your X is an activator, okay, activator, okay, and you should know it's things like NH2, okay, OH. It's a bit slow again, but it's okay. Okay, right? Or R. Now, so example here, NH2. Okay. Now, if you want to put an electrophile inside here, you learn about positioning, right? It will sit at position 2, 4, 6. Okay, so I'm not going to repeat it. Okay, position is like this. Now, they will probably ask you to describe what about the rate of this reaction. Okay, the rate of this reaction is faster, all right, compared to just a ring, and you do the first substitution. Because this is the second substitution. The first substitution was obviously NH2 on the ring. Okay, this is the second substitution where you're trying to put in another electrophile symbol E, and this equation will be faster. All right, why? It's because the NH2 on the ring is an activator. It will make this electrophilic substitution faster, and perhaps probably they'll ask you why. Okay, now if you want to explain why, I'll just type it out here. Okay, now what happened here is the lone pair electrons on nitrogen atom will be delocalized into the ring. Okay, and this will, there is high electron density in the ring, and it, let me just expand the box. Okay, therefore, there is high electron density in the ring, and the ring is susceptible to electrophilic attack. Okay, hence, the rate of this reaction is higher. Okay, so when you have a lone pair over here, on the nitrogen or the oxygen on the OH, can you see? All right, so be it NH2 or OH, okay, the O also got lone pair, right? The benzene ring will withdraw the lone pair and the lone pair will be delocalized into the ring. So when the lone pair is delocalized into the ring, all right, your ring now will have an increase in electron density because first we already learned that there is high electrons moving in the ring. So this is the side view, this is the top view. So you have the electrons running, the 3 pi bond electrons are running. Okay, now, so this is side view. So when you throw a lone pair into the ring, so there is more electrons inside the ring, therefore high density. Now, when you're rich in electron, a lot of negativity, you will attract something positive. Or in other words, some species that is electron deficient. All right, you know, right? Electrophilic or electrophile is a species that is deficient in electrons. So if you're rich in electron, you will attract a species that is deficient in electrons. That is why when you attract very fast, the rate occurs faster. Understand? Okay, yeah. So that is if you are the OH and H2 type, okay, where your so-called activators have a lone pair. Actually, any atom that has a lone pair inside it will be able to delocalize that electron into the ring. They will be able to delocalize. Okay, so the very straightforward example here would be NH2, okay, or the OH. Okay, I'm going to draw the lone pair very obvious. Okay, here. Like this. Now, to add up a little bit more, which is, you know, a little bit extending from your syllabus or from the Cambridge syllabus, all right, I'd like to extend a little bit more beyond the syllabus here. Okay, now, your lone pair is delocalized into the ring, right? Okay, and this effect is actually called as the conjugated effect. All right, we are conjugation. So maybe under the text here. Okay. All right, conjugation effect. This is the action. When lone pair is being delocalized into a ring, all right, we call this a conjugation effect. Okay, now because why I have to bring this thing up is because I want to separate this compared to your third activator called R. This will be easier for you all, okay, who has already finished AS. Now, your alkyl group R is also an activator. Yes, it will also direct any incoming electrophile to position 2, 4, 6. All right, but the effect, all right, exerted by the alkyl group, everybody know if you're in R group, right? The effect is called a positive inductive effect. Okay. Yes, all right. Positive inductive effect. Okay. Now, I personally think it will be good for you all to know, all right, especially for the positive inductive effect by alkyl group, because everybody know the alkyl group are electron donating group. Electron donating group will exert a positive inductive effect. So they will push electron nearer to the ring, and this effect is called as a positive inductive effect. But if you have a lone pair, all right, on your atom, the way they donate electron in is via conjugation effect. So among the 3 activators, NH2 OH, the way they behave as an activator, okay, is due to conjugation effect, which means lone pair electron will be delocalized into the ring. Okay, and if you are the LQ type core, R, any R, therefore the way they donate electron in way is via positive inductive effect. Okay, so your first statement have to be according to which is your activator. All right, so the first statement over here, statement number 1, okay, you can treat it, if this is NH2, then you use N. If this is OH, then you use O. And if this is an R, you use the R. All right, you cannot say lone pair on the LQ group. No, there's no lone pair on the LQ group. You just say the LQ group is a electron donating group. It will exert a positive inductive effect. Then the second statement is the same. And then the third statement is the same. All right, so askers have asked this question before. Okay, so most of the time they will, focus on how they increase the rate, okay, by making them more susceptible to the electrophile. And actually, the keyword here is the delocalization of the lone pair electron on the nitrogen and oxygen, or the positive inductive effect of the LQ group. Is this a must know in the syllabus? I would say it's yes. All right, because you learn positive inductive effect, okay, in AS. All right, and then oxygen and nitrogen will be delocalized into the ring, also need to know. All right, it's just that the conjugation effect term is not made known to you. All right, yeah, so I repeat now, conjugation effect is not made known to you, but the lone pair on electron or lone pair electron on the nitrogen, oxygen, right, that one you have to know. Okay, yeah, now what about the other side? If you are a deactivator, okay, so normally you don't need to know on the activator. The activator is because they are mostly electron withdrawing group. They will withdraw electron from the ring. All right, therefore it will decrease the electron density and making it less susceptible. So what you want to do here is you want to change all your description, but you don't need to know for the first one. It's because due to electron withdrawing group here, okay, you don't need to know what kind of effect, okay, but if you really want to know, most of the time is via negative inductive effect. Just so you know, all right, electron withdrawing group will exert a negative inductive effect, electron donating group will exert a positive inductive effect. So if you're playing with deactivators, because most of the time they are electron withdrawing group, they will exert a negative, okay, negative inductive effect. Okay, all right, so that's your first statement. Now you don't need to know too detailed. Okay, therefore, there is a low electron density. Please change high to low in the ring, and the ring is less susceptible. When you are less electron rich, right, you will not attract for electrophile very quickly. Less electron, that means you are less negativity. Less negativity means you will not attract positive so fast. So-called the common sense. All right. So if you will not attract electrophile that fast, that means the rate of the reaction will be slower. Okay. Yeah. Now, so therefore, I have covered in terms of the position, which is more important. Rate will come second, because normally rate will ask you in a maybe 1 to 2 marks question where students are required to explain. All right, and you can use my point 1, point 2, point 3 to explain. Okay, but more emphasis will be on activator, how they so-called activate the ring to make the rate of reaction faster. Okay, yeah, that's all you need to know when it comes to rate. Okay, and then position. Okay. So if you want to zoom up, zoom out to show you the whole thing. All right. Take a look over here. You go into a screenshot over here, and then the rate like this. Okay. And therefore, I'll see you in the next video, and we're going to discuss on halogenal and rings, which is our exception case.